At first, distance seems simple. Move away from the sun, and it should quickly become another star. But the numbers tell a stranger story. Near Neptune, the sun is already shrinking toward a point. At 100 astronomical units, its disk is gone to the naked eye. Yet even 1 light-year away, it would still outshine Sirius. Only after crossing several light-years does our familiar sun begin to look truly ordinary. If calm journeys like this help make space feel a little clearer, a like, a subscription, or a share helps calm space science continue creating them. And thank you for spending part of your time here. Where in the world are you watching or listening from? And what time is it there? Perhaps this is part of a quiet evening, a study session, or the last few minutes before sleep. Leave a comment and add your place and time to the map of listeners. For now, Earth is still close behind, and the sun still fills the sky. The journey outward begins there. At Earth's distance, the sun does not look like a star in the ordinary nighttime sense. It looks like a world-sized presence suspended in daylight, a brilliant disk about half a degree across, wide enough to show a definite circular edge and bright enough to erase almost every other star from the sky. That appearance feels natural only because life on Earth has never known anything else. The sun rises large enough to be recognized as a shape, sets large enough to keep that shape, and pours so much light across the atmosphere that the blue daytime sky becomes part of its visible effect. Yet none of this reflects an unusual physical size for a star in any simple way. The sun is a fairly ordinary star by many stellar measures. What makes it extraordinary in Earth's sky is distance. Earth orbits roughly 1 astronomical unit from the sun, a separation of about 150 million kilometers, and on the scale of the galaxy that is almost no distance at all. The nearest other stars are not merely thousands or millions of times farther away in some vague sense. They are so much more distant that their disks collapse below the resolving power of unaided human vision, leaving only points of light. The sun, by contrast, is close enough that its surface spans roughly 30 arc-minutes of sky. That angular width is not a measure of the sun's true diameter. It is a measure of how large that diameter appears from a particular location. A coin held nearby can cover the moon. A mountain on the horizon can appear smaller than a hand. Apparent size depends on the relation between an object's physical scale and the distance separating it from the observer. And the sun is the most familiar astronomical example of that geometry. Its true diameter is about 1.4 million kilometers. Enormous compared with any planet. But the important fact for the sky is that Earth sits close enough for that diameter to occupy a measurable patch of vision. The result is the disk that defines daylight. Even this familiar disk is already a perspective effect. Nothing about the sun itself announces that it must occupy half a degree of anyone's sky. Move the observing point outward, and the sun does not contract. Its surface does not fold inward, and its physical radius does not change. Only the angle it subtends becomes smaller. That distinction is the first step toward understanding how the sun can eventually become indistinguishable in appearance from the stars around it. At Earth, however, there is still no ambiguity. The sun is not simply the brightest point in the sky. It is in a different visual category. Its apparent visual magnitude is about -26.7, a value that places it vastly beyond the brightness of any star visible at night. The magnitude scale runs backward, so more negative values mean greater apparent brightness. And the difference between the sun and a bright star is not a small extension of the same experience. It is immenser. Sirius, the brightest star in Earth's nighttime sky, is brilliant by stellar standards, as seen from here. Yet daylight overwhelms it because the sun sends so much more visible light into the atmosphere and the eye. The atmosphere then scatters part of that sunlight in every direction. Shorter visible wavelengths are scattered efficiently, helping produce the blue sky that hides most stars during the day. In that sense, the sun dominates not only by being bright at its own position, but by changing the appearance of the entire sky around it. Its light creates the background against which nearly everything fainter disappears. That domination also shapes human intuition. The sun is experienced as a luminous disk because its angular size is resolvable, as a source of heat because its energy flux at Earth is high, and as the organizer of day and night because Earth rotates beneath a sky flooded by its light. All three impressions weaken with distance. but they do not weaken in exactly the same way. The disk shrinks according to geometry. The received light falls according to the spreading of radiation through space. The warmth diminishes with that same decline in energy per unit area. Long before the sun becomes faint enough to resemble a normal star, its visible disk will become too small for unaided eyes to recognize clearly as a disk at all. That difference between shape and brightness is easy to overlook while standing on Earth, because both properties are extreme at once. The sun is large in apparent angle and overwhelming in apparent brightness. So the mind naturally bundles those traits together as if they were one thing. They are not. They separate as soon as distance begins to increase. Earth, therefore, provides the starting condition for a gradual transformation rather than a special category that persists forever. Close to home, the sun is a nearby stellar surface. Its photosphere, the visible layer from which most of its light escapes, is spread across a broad enough angle that telescopes can map sunspots, granulation, faculae, and the changing structure associated with solar activity, even without a telescope, and without looking directly at it. Its geometric presence is obvious through safe projection and through the sharpness of its circular outline during events such as solar eclipses. The Moon can cover the solar disk because the two bodies happen to have similar angular sizes in Earth's sky, despite having radically different physical diameters and distances. That coincidence is another reminder that what fills the sky is determined by angle, not by true size alone. From farther out, the balance changes. The Moon would no longer matter as a reference point. Earth would become a small inner world, and the solar disk would tighten steadily toward the scale of a bright point. But at 1 astronomical unit, the sun remains so close that its stellar nature is almost concealed by familiarity. Stars are often imagined as distant specks, while the sun is imagined as something separate, yet physically the distinction is one of viewpoint. The sun is what a star looks like when a rocky planet orbits near enough to receive strong visible light and enough energy to sustain a warm surface environment. The nighttime stars are what other suns look like when interstellar space is allowed to intervene. This makes Earth's view unusually revealing. Every sunrise is a close-range observation of a star, not close in any terrestrial sense, but close enough astronomically that its surface has width. Its light has overwhelming intensity, and its energy controls the climate of an entire planet. The great change begins only when that privileged distance is surrendered. At first, very little seems dramatic. A journey outward by a small fraction of an astronomical unit merely makes the disk a little smaller and the sunlight a little weaker. The transformation does not occur at a border. There is no shell around the solar system beyond which the sun suddenly clicks from disk to star. Instead, the familiar object is dismantled gradually by perspective. Its edge becomes harder to distinguish. Its glare occupies less sky. The planets gather closer to its apparent position. Eventually, the geometry that makes the sun look special begins to resemble the geometry that governs every other star. The most important fact at the beginning, then, is not that the sun is intrinsically unlike the points of light seen at night. It is that Earth is extraordinarily near one particular star. From this distance, the sun appears to belong to a category of its own, because proximity enlarges its face and concentrates its brightness into an experience no other star can match from Earth. The journey outward will remove those advantages one by one. First, the disk will shrink, then its dominance will soften, and only much later will its brightness fall into the range associated with ordinary stars. The starting sun is therefore less a permanent object of the sky than a close-up view, and distance is the lens that will slowly pull that close-up away. The sun does not need to change for its appearance to change completely. Distance alone is enough. Once an observer begins moving outward from Earth's orbit, two transformations start at the same time, and although they are linked to the same increase in distance, they do not affect perception in quite the same way. The first is geometric. The sun's angular diameter becomes smaller because the same physical object occupies a narrower angle in the sky. The second is photometric, meaning it concerns received light. The solar energy arriving at a given area falls because that light spreads through an ever larger region of space. These two effects are easy to confuse, while the sun is still large and painfully bright. But separating them is essential because the answer to when the sun becomes just another star depends on which effect matters most. Angular size follows a particularly simple pattern once the observer is much farther from the Sun than the Sun is wide. Double the distance, and the apparent diameter becomes about half as large. Move 10 times farther away, and the angular diameter falls to about 1/10 of its original value. At Earth, the solar disk spans roughly 30 arc-minutes. At 10 astronomical units, it would span only about 3 arc-minutes. At 100 astronomical units, it would fall to roughly 18 arc-seconds. The actual Sun has not shrunk by a single kilometre. Its photosphere has the same broad surface, the same radius, and the same physical structure. Only the viewing geometry has changed. This is the same reason a distant mountain appears smaller than a nearby building, even when the mountain is vastly larger. The eye does not measure true diameter directly. It measures angle. That distinction becomes decisive for stars because the human eye has limited angular resolution. 2 points separated by a very small angle blur together, and a circular object below a certain apparent size cannot be recognized as a disk without optical assistance. The Sun, therefore, reaches a point-like appearance much sooner than it reaches ordinary stellar brightness. That is the first major separation in the journey. A point of light is not necessarily faint. It only means the source is too small in angle for its shape to be resolved. A distant planet, a bright artificial light, or a star can all appear point-like for the same geometric reason, even though their physical properties differ enormously. The Sun gradually enters that category as distance removes the visible width of its disk. Brightness follows a different rule. Light leaving the Sun spreads outward in all directions through space. At a given distance, the same total solar power has been distributed across the surface of an imaginary sphere centered on the Sun. As the radius of that sphere increases, its surface area grows with the square of the radius. That produces the inverse square law. If the distance from the Sun doubles, the received energy per unit area falls to 1/4. If the distance increases tenfold, the received energy falls to 1/100th. At 100 times Earth's distance, the sunlight is reduced to 1/10,000th of the intensity received near Earth. This decline is rapid, but the starting point is so extreme that even enormous reductions leave the Sun extraordinarily bright compared with stars. That is why the visual transformation feels uneven. The disk can become tiny while the light remains dominant. Angular diameter decreases in direct proportion to distance, while energy per unit area decreases with the square of distance. The two quantities therefore separate steadily as the journey continues outward. This has another consequence. The environment illuminated by the Sun changes before the Sun itself looks ordinary. At greater distances, surfaces receive less energy. Temperatures associated with direct solar heating fall. Shadows remain sharply defined because the Sun is still a concentrated source. But the overall level of illumination declines. What was broad daylight near Earth becomes weaker illumination farther out, even while the source responsible for it can still be brighter than anything normally seen in a terrestrial night sky. Human visual intuition is not well adapted to this range because ordinary experience covers only modest differences in distance. A lamp across a room does not become star-like. A city seen from a hill does not test the limits of angular resolution in the same way. Interplanetary distances allow one familiar object to pass through regimes that have no everyday equivalent. First, it is a disk. Then, it is a smaller disk. Then it becomes a brilliant point. Later that point weakens into something comparable with the brightest stars. Later still it blends into the wider stellar population. Each stage is governed by the same physical rules. Yet each produces a different visual category. The magnitude system provides another way to describe the brightness change. Apparent magnitude measures how bright an object appears from a particular location, with smaller and more negative values corresponding to greater brightness, because the scale is logarithmic rather than linear. Equal changes in magnitude represent equal ratios of brightness rather than equal amounts of light. This is useful for astronomy because the sky contains objects separated by enormous brightness ranges. The Sun begins near an apparent visual magnitude of -26.7 as seen from Earth. That value is so extreme compared with ordinary stars that reducing its brightness by factors of hundreds, thousands, or even millions still does not immediately push it into the familiar nighttime range. Distance can make the Sun much dimmer and yet leave it visually exceptional. That is why a simple question about when it becomes another star does not have a single geometric answer. If the criterion is whether the Sun still looks like a disk, The transition happens within the broad territory of the outer solar system. If the criterion is whether it shines like a bright star, the required distance is vastly greater. If the criterion is whether its brightness becomes unremarkable among the stars, the observer must travel farther still. These thresholds do not coincide because apparent size and apparent brightness encode different information. One describes how much angle the source occupies, the other describes how much light reaches the observer. A large but dim object and a small but bright object can therefore produce very different impressions, even when both are distant. The Sun's journey from solar disk to stellar point is a particularly clean demonstration of this difference, because its intrinsic output stays essentially constant across the imagined voyage. There is no need to invoke stellar evolution, fading fuel, or changing surface temperature. Over the travel distances being considered, the Sun can be treated as the same star throughout. The transformation belongs to the observer. Perspective steadily strips away the features that make the Sun feel unique. Its edge becomes harder to resolve. Its surface structure becomes inaccessible without better instruments. The planets appear to crowd closer around its position in the sky because their orbits occupy smaller and smaller angles when the entire solar system is viewed from farther away. Meanwhile, the intensity of its light keeps falling according to the inverse square law, predictable at every step. Nothing dramatic happens at any one boundary. There is only a continuous reduction in angle and flux. Yet perception converts that smooth mathematical decline into a sequence of qualitative changes. A circle becomes a point. A source of daylight becomes an isolated brilliance. A dominant brilliance becomes a bright star. A bright star becomes an ordinary one. Eventually, even that ordinary star approaches invisibility to unaided eyes. The remarkable part is how widely separated these stages are. Losing the disk does not mean losing the Sun's dominance. Weakening the sunlight does not immediately make the source visually ordinary. The geometry reaches one threshold while brightness remains far from another. That separation sets the structure for everything that follows. Because each new distance will test a different part of the same transformation, the Sun is already becoming smaller as soon as the journey begins. But becoming smaller is only the first step toward becoming stellar. Mars offers the first useful change of perspective because the Sun is already noticeably smaller there. Yet nothing about it has become remotely ordinary. The planet follows an orbit farther from the Sun than Earth does. So the solar disk occupies less of the Martian sky, and the sunlight reaching the surface is weaker. But the transformation remains modest enough that the familiar structure of a sun is still obvious. From Earth, the solar diameter is close to 30 arc-minutes. From the average distance of Mars, that apparent diameter falls to roughly 2/3 of the terrestrial value, varying somewhat as Mars moves through its elliptical orbit. The disk is smaller, but it is still plainly a disk. Its edge remains geometrically distinct. Its position determines the direction of strong illumination, and its brightness still overwhelms every normal star. This is an important early stage because it shows how slowly the visual identity of the Sun begins to erode. Interplanetary distances sound immense when measured in kilometers. Yet even after moving tens of millions of kilometers beyond Earth's orbit, the observer remains extremely close to the star by astronomical standards. Mars receives substantially less solar energy per unit area than Earth, following the inverse square decline, and that weaker input helps shape its colder climate. The visual experience, however, is not equivalent to looking at a bright star. The Sun still functions as an extended source whose width can be measured directly, and its light still defines a daytime environment. Martian skies complicate the appearance because the atmosphere contains suspended dust that scatters sunlight differently from Earth's air, often producing colours and brightness patterns unfamiliar from the terrestrial surface. But those atmospheric effects do not change the basic geometry. The Sun remains a small circular source, not a stellar point. Moving farther outward toward the asteroid belt continues the same trend without creating a sharp transition. The main asteroid belt occupies a broad region between Mars and Jupiter, and across that territory the Sun steadily contracts in angular size. At twice Earth's distance from the Sun, the disk is about half as wide as it appears from Earth. At 3 times Earth's distance, it is about 1/3 as wide. The apparent diameter therefore moves from something comparable with the familiar solar and lunar disks toward an increasingly compact circle, but the eye is still dealing with a resolved object rather than an unresolved star. Brightness falls faster than angular diameter because received light follows the square of distance. At twice Earth's distance, sunlight is reduced to about 1/4 of the terrestrial level. At 3 times the distance, it is reduced to about 1/9. These changes are large enough to alter the lighting of surfaces and the equilibrium temperatures of small bodies, yet they still leave the sun astonishingly intense compared with the stellar background. This is where ordinary intuition can become misleading. A reduction to 1/4 or 1/9 sounds severe, and physically it is significant. But the sun begins from such an extreme brightness that these fractions remain far above the brightness of nighttime stars. The asteroid belt, therefore, does not feel like a region where the sun has joined the stars. It is a region where the sun has become smaller and the surrounding darkness has become more prominent, while the central source of light still holds a completely different visual status from everything else. An asteroid surface in this region would not be illuminated as brightly as Earth, but the direction of sunlight would remain unmistakable. Shadows would still reveal a single dominant source. Reflective rock and dust would still respond primarily to solar illumination. Against black space, the sun would appear less broad than it does from a terrestrial landscape, yet still too large and too bright to confuse with a distant stellar point. The distinction can be understood through the way an extended disk behaves. When a source has visible width, light arrives from slightly different directions across that width. This influences the sharpness of shadows and the appearance of occultations, where one body passes in front of another. As the solar disk becomes smaller with distance, those effects become more concentrated. But throughout the inner solar system, the sun still has enough angular extent to preserve its identity as a disk. The fact that it remains physically unchanged makes the transformation particularly clean. No stellar process is involved. The sun is not dimming because its core has altered, and it is not shrinking because its outer layers have contracted. The entire change is caused by geometry and dilution of light. Mars and the asteroid belt act as the first extended demonstration of those rules, under conditions far removed from Earth, but still nowhere near interstellar space. They also reveal an important asymmetry between human measures of distance and astronomical ones. Hundreds of millions of kilometers represent an enormous voyage for spacecraft, but only a small adjustment in the perspective on a star. The sun's true scale is so large, and Earth's original position so close, that considerable outward travel is required before its apparent diameter becomes genuinely tiny. The same is true of brightness. A spacecraft moving beyond Mars enters an environment where solar panels receive less energy. Thermal conditions become more severe, and the background of space feels increasingly dominant. Yet the sun itself remains visually commanding. Each additional astronomical unit produces a measurable change, but not yet a categorical one. At the inner edge of the asteroid belt, the disk is smaller than from Mars. Near the middle, smaller again. Toward the outer belt, approaching Jupiter's domain, the circular form becomes increasingly compact. Still, the path from a solar disk to a star-like point is not complete. The eye can continue to assign width to the source under suitable conditions, and optical instruments can do so with ease. This matters because the question of when the sun looks like another star is partly a question about resolution. Stars appear point-like not because they are physically small, but because their angular diameters are too tiny to resolve without specialized instruments. Many stars are physically larger than the sun, sometimes enormously larger, yet their distance compresses them into points. The outward journey reverses that perspective on the sun. Instead of bringing another star close enough to reveal its disk, it carries the observer far enough away that the sun begins to lose its own. Mars is too close for that loss to be dramatic. The asteroid belt advances the process, but does not finish it. The solar face is reduced, the sunlight is weaker, and the surrounding blackness occupies more of the visual scene, yet the source itself remains unmistakable. There is still a circular body of light where ordinary stars offer only points. There is still enough flux to dominate illumination. There is still no plausible confusion between the Sun and Sirius, Vega, or any other bright star scattered across the distant sky. The transformation becomes more interesting precisely because it remains incomplete. The first few 100 million kilometers outward demonstrate that immense travel does not automatically produce an interstellar view. The solar system is large enough for the Sun's appearance to change substantially while remaining entirely solar in character. By the time the asteroid belt begins to give way to Jupiter's domain, the disk has contracted enough for the next stage to become more noticeable. The Sun is no longer the broad presence familiar from Earth, but neither has it surrendered its shape. The threshold ahead is not one of disappearance, but of compression, where the disk finally becomes small enough that brightness and form begin telling two very different stories. Near Jupiter, the geometry of the solar system finally pushes the Sun into a noticeably different visual regime. The planet orbits at an average distance of a little more than 5 astronomical units, far enough that the solar disk spans only about 1/5 of the angle it does from Earth. What appears as a broad half-degree circle in the terrestrial sky contracts to only a few arc-minutes across. The Sun is still resolved as a disk under suitable conditions, but its familiar proportions are gone. It has become compact enough that the surrounding blackness seems to claim far more of the sky, and the gap between what the Sun looks like and how much light it still delivers becomes increasingly important. The physical star is unchanged. Its photosphere is still nearly 1.4 million kilometers wide. Its surface still radiates with essentially the same temperature, and its core continues producing energy at the same rate for every practical purpose in this journey. Only the observer has moved. Yet that movement is now large enough to make the Sun feel less like the commanding disk known from Earth, and more like a concentrated source whose size must be judged carefully. At Jupiter's orbit, sunlight is reduced to roughly 1/25 of the intensity received at Earth, because the distance has increased by about a factor of 5, and the inverse square law acts on that change. This is a major reduction in energy. Solar panels produce far less power. Surfaces warmed by direct sunlight reach much lower temperatures, and the outer solar system begins to take on the thermal character associated with cold giant planets and icy moons. But visually, 1/25 of terrestrial sunlight is still enormous compared with starlight. The Sun remains the unquestioned source of illumination. It can cast strong shadows, it can brighten cloud tops and icy surfaces, it can still overwhelm ordinary stars near its position in the sky. The reduction is therefore physically dramatic without being enough to make the Sun ordinary. This difference between energy decline and visual category is one of the most revealing features of the journey. Human perception tends to associate a smaller source with a fainter one, but the Sun resists that intuition. Its apparent diameter has shrunk by a factor of about 5, while the light falling on a surface has fallen by roughly a factor of 25. Even after that substantial dimming, the starting brightness was so extreme that the result remains far beyond the brightness of the brightest nighttime stars. The Sun's disk also still carries information that a true stellar point does not. With proper optical equipment, its circular edge is easy to distinguish. Solar activity can still be mapped. Transits and occultations can still reveal the finite size of the source. The image is smaller, but it is not yet compressed into an unresolved point. The Galilean moons of Jupiter make this geometry especially tangible. These large moons pass through Jupiter's shadow, cross in front of the planet, and move through a system whose lighting is entirely set by the distant Sun, because the Sun appears smaller from Jupiter than from Earth. The geometry of shadows differs from the familiar terrestrial case. The angular size of the illuminating source affects the width of partial shadow regions and the sharpness of transitions between full light and eclipse. The Sun is already beginning to act more like a compact lamp in the sky, even while remaining a measurable disk. This is a subtle but important stage. The question is no longer whether the Sun is getting smaller. That is obvious. The deeper issue is whether smallness alone is enough to make it look stellar. At Jupiter, the answer remains no. A star in the night sky has no visible surface to unaided eyes. It is a point defined almost entirely by brightness and colour. The Sun near Jupiter is approaching that appearance, but its angular diameter is still too large to erase its extended nature completely. The distinction becomes easier to understand by comparing it with the limits of vision. The human eye can separate detail only down to a certain angular scale, and that threshold depends on contrast, brightness, atmospheric conditions, and the eye itself. A source, a few arc-minutes wide, is close enough to this range that extreme brightness and glare can make its true edge difficult to judge directly, especially without optical filtering. Yet geometrically, the disk is still present. Instruments have no difficulty resolving it. The Sun at Jupiter is therefore not yet a star in the strict visual sense, but it is no longer visually similar to the Sun from Earth either. It occupies an intermediate state where familiar identity is being compressed without being erased. Jupiter itself reinforces the scale change. The giant planet is so large that its moons orbit across distances comparable to entire planetary systems in miniature. Yet all of that complexity unfolds under a sun that appears unexpectedly small. The star still determines every illuminated hemisphere and every cast shadow, but it no longer dominates by apparent size. This separation between visual size and physical authority is striking. A source can become tiny in angle while remaining the central energy supplier for a vast planetary system. The same principle applies even more strongly, farther out. By the time the observer reaches Saturn, Uranus, and eventually Neptune, the disk continues shrinking in direct proportion to distance. Its role as an energy source weakens with the square of that distance. The result is a gradual uncoupling of three ideas that are almost inseparable on Earth: the Sun as a large object, the Sun as an intensely bright object, and the Sun as the dominant source of planetary energy. Near Jupiter, the first of these is already fading quickly, the second remains overwhelming, and the third is still absolute, even though the energy available per unit area has dropped sharply. The sky itself would reflect that new balance. Without an atmosphere like Earth's to scatter sunlight broadly, space remains black even when the Sun is present. Against that black background, the Sun appears as a compact, fierce source rather than as the centre of a blue dome. This is not because Jupiter's region is truly dark in the sense of receiving little visible light compared with a terrestrial night. It is because empty space does not scatter the light into the observer's line of sight. A nearby illuminated moon or spacecraft surface can still appear bright, while the sky surrounding the Sun remains black. That visual combination makes the shrinking disk easier to appreciate conceptually. The Sun is becoming isolated rather than blended into daylight. It begins to resemble the arrangement associated with stars, a bright point-like source against darkness. Yet the resemblance is incomplete because the source is still too broad and far too bright. The difference is quantitative, but perception turns it into a qualitative boundary. Jupiter therefore marks a useful middle stage between the broad solar disk of the inner system and the near-point source of the distant outer system. The transformation is no longer subtle enough to ignore. The Sun has contracted to a fraction of its terrestrial width, and its light has weakened by more than an order of magnitude. But neither change has gone far enough to make it ordinary. What Jupiter reveals is not the moment when the Sun becomes a star. It reveals how much distance is required even to begin stripping away the visual privileges of being nearby. The disk is smaller, the illumination is weaker, and the black sky is more prominent, yet the source still commands the scene. Farther outward, that last visible width will continue to collapse until the question of shape is nearly settled. Brightness, however, will remain stubbornly exceptional. At Neptune's distance, the Sun finally approaches the visual scale at which its familiar disk begins to give way to something much closer to a point. Neptune orbits roughly 30 astronomical units from the Sun, and that single fact changes the geometry dramatically. A solar disk that spans about 30 arc-minutes from Earth contracts to roughly 1 arc-minute across when seen from the neighbourhood of Neptune. The physical Sun remains exactly the same size, but it now occupies only a tiny fraction of the observer's field of view. At this distance, the distinction between a small disk and a point of light becomes increasingly dependent on the resolving power of the eye and the conditions of observation. The Sun has not literally become point-like in a geometric sense. Its photosphere still has a measurable angular diameter, and a telescope can resolve that diameter without difficulty. But to unaided vision, especially with the complications of glare, such a compact source begins to lose the obvious circular identity it has near Earth. This is one of the first distances where the title question becomes visually meaningful. The Sun is starting to look stellar even though its brightness remains nothing like that of an ordinary star. That mismatch is extreme. At roughly 30 astronomical units, the sunlight reaching a surface has been reduced by about the square of 30 compared with the amount received at Earth. The reduction is therefore close to a factor of 900. Such a decline has enormous consequences for the environment. Solar heating is weak. Icy surfaces remain cold. The giant planet and its moons exist in a realm where the Sun supplies far less energy per unit area than it does to the inner planets. Yet a decrease by a factor of hundreds is still not enough to bring the Sun anywhere close to ordinary stellar brightness, because its starting point is so exceptional. Its apparent magnitude from around Neptune is still roughly -19. On the magnitude scale, that places it vastly above Venus, Sirius, or any familiar nighttime star seen from Earth. It is dimmer than the terrestrial Sun by an enormous amount, but it remains a fiercely bright object. That combination creates a visual state that does not have a close everyday equivalent. The source is tiny, nearly star-like in form, yet overwhelmingly bright in intensity. This distinction matters because human perception often treats point-like appearance and stellar brightness as if they belong together. In most nighttime experience, they do. Stars are points, and they are faint compared with the Sun. Near Neptune, those two associations separate. The Sun can look like a concentrated point while still delivering enough light to dominate the entire sky as a source. The darkness around it does not mean the source itself has become weak. Empty space remains black because there is little material available to scatter light toward the observer. A spacecraft surface, a moon, or the upper atmosphere of Neptune can still be illuminated clearly by sunlight, even while the surrounding sky stays completely dark. Against that background, the Sun would appear less like the broad, radiant body familiar from Earth and more like an isolated, intensely bright spark. The absence of a blue terrestrial sky would make the compactness of the source even more apparent. The Sun would no longer seem to occupy a broad region of daylight. It would instead sit inside darkness as a concentrated emitter whose light is revealed mainly by whatever it strikes. This is a useful reminder that daylight is not simply the presence of the Sun above the horizon. On Earth, atmospheric scattering spreads sunlight through the sky. In airless or nearly airless environments, the sky can remain black even under strong illumination. The outer solar system pushes this contrast further because the Sun is both geometrically smaller and energetically weaker. Neptune itself receives only a small fraction of the solar energy available to Earth, and its atmosphere is shaped by a balance of processes that cannot be understood as a simple continuation of terrestrial sunlight. Internal heat also matters for the planet's energy budget, reinforcing how far the system has moved from the warm, sun-dominated conditions of the inner planets. Visually, however, the Sun still controls direction. Surfaces facing it are illuminated. Surfaces turned away fall into shadow. The difference between day and night remains tied to the same star. But the source that creates that contrast has become almost pin-like, at roughly 1 arc-minute across. The solar disk is near a scale where unaided human vision is no longer comfortably resolving its shape under ordinary circumstances. The exact perceptual threshold is not a rigid boundary, because vision depends on contrast, brightness, optical quality, and the characteristics of the eye. The Sun's brilliance also complicates direct judgment of its edge, but the physical trend is unmistakable. The broad circle has been compressed by a factor of about 30 compared with its earthly appearance. This is far enough that the concept of a solar face begins to lose practical meaning without optical aid. What remains is a brilliant direction in the sky rather than an obvious circular surface. The transition is gradual, but Neptune provides a compelling landmark because the angular scale has now reached roughly the same order as the finest detail the unaided eye can normally resolve. The Sun therefore stands near a perceptual threshold, even though it remains far above any stellar brightness threshold. This is the central tension of the outer solar system. Shape reaches the stellar regime long before luminosity does. The same inverse relationship that steadily reduces angular diameter has now done enough work to erase much of the Sun's visual width. The inverse square law, meanwhile, has reduced the received light far more dramatically in a numerical sense. Yet the result is still extraordinarily bright because the original flux at Earth was so great. The two transformations are proceeding together but arriving at perceptual milestones at very different distances. From Neptune, the Sun has lost much of its identity as a disk, while retaining its identity as the dominant light source. That difference would also affect the way the wider solar system appears. The inner planets occupy very small angles close to the Sun's position when viewed from so far away. Earth itself lies deep toward the central glare, difficult to separate without careful observation and suitable instruments. The planetary architecture that appears spacious from within begins to compress when viewed from the outer edge of the major planetary system. The Sun still anchors that compressed structure, but its own apparent width is now tiny. A large system is beginning to look geometrically compact around a small point of light. This pattern will intensify beyond Neptune. Moving into the Kuiper Belt, the Sun's disk continues shrinking below an arc-minute. At greater distances, even instruments require more angular resolution to separate the photosphere cleanly. Yet the Sun continues to remain astonishingly bright compared with the stellar background for a very long time. That persistence is what makes the journey outwards so counterintuitive. The visual shape associated with a nearby star is lost relatively early. The brightness associated with a nearby star survives vastly farther. Near Neptune, these two facts finally stand side by side in a clear form. The Sun can already begin to look almost like a star, while still shining with an intensity that no ordinary star in Earth's night sky comes close to matching. The familiar solar disk is nearly gone, but the familiar solar dominance is not. Beyond Neptune, the Sun enters a region where its appearance finally becomes deceptive. The Kuiper Belt begins around the orbit of Neptune and extends outward through a broad population of icy bodies, dwarf planets, and small remnants left from the formation of the solar system. Across this region, roughly 30 to 50 astronomical units from the Sun, the solar disk continues to shrink from about 1 arc-minute toward little more than half that width. To an unaided eye, the distinction between a very small disk and a brilliant point becomes increasingly difficult to preserve. The Sun has not become physically smaller, and its surface remains perfectly resolvable with suitable instruments. But its ordinary visual identity is slipping away. What remains is a source that looks much more like a star in shape, while behaving nothing like one in brightness. That difference is the defining feature of the Kuiper Belt view. From Earth, a star is understood almost entirely as a point of light. Its surface is hidden by distance, its diameter inaccessible to normal vision, and its brightness limited enough to sit comfortably against the darkness of the night sky. The Sun in the Kuiper Belt satisfies only the first part of that experience. Its angular diameter has been reduced enough that its edge no longer announces itself clearly to the eye. Yet the amount of light reaching an observer is still enormously greater than the light received from even the brightest stars seen from Earth. At 40 astronomical units, for example, the solar energy per unit area is reduced by roughly a factor of 1600 compared with Earth. That decline is severe for anything that depends on sunlight. Surfaces warm less efficiently. Solar power becomes harder to collect. The contrast between illuminated and unilluminated terrain persists, but the overall energy environment is cold and sparse. Even so, the Sun remains far too bright to blend into the stellar background. This is possible because the brightness at Earth begins from such an extreme level. Reducing something overwhelmingly bright by a factor of thousands does not automatically make it ordinary. The Sun can lose almost all of the illumination familiar from the inner solar system and still remain visually dominant as a point source. The Kuiper Belt therefore exposes a useful failure of intuition. The mind tends to treat a star-like shape as evidence of stellar distance, but point-like appearance says only that an object is unresolved. It does not say how bright the object must be. A tiny angular diameter can belong to a faint star, a distant planet, or an intense source that is simply too small in apparent width for the eye to separate. The Sun has now crossed into that category. Its geometry has become stellar before its brightness has done the same. This mismatch becomes clearer when the surrounding environment is considered. The Kuiper Belt is not a narrow ring with a sharp outer wall. It is a broad and structured region containing populations with different orbital histories, including objects whose paths have been shaped by Neptune's gravity. Pluto moves through this outer territory on an eccentric orbit, and many smaller bodies spend their long years under sunlight far weaker than anything experienced by the inner planets. From the surface of such a world, the Sun would occupy almost no obvious area in the sky. It would be a concentrated point set against blackness, and the landscape beneath it would still carry unmistakable evidence of its direction. An icy plain would brighten on the side facing the Sun. Relief would cast shadows. A rotating body would still pass through day and night. Yet the source responsible for all of this would no longer resemble the broad disk that defines daylight on Earth. The physical effect of sunlight and the visual impression of the Sun would have separated almost completely. This separation is one reason the phrase, "just another star," becomes ambiguous. If the phrase refers only to form, The Kuiper Belt comes close to satisfying it. If the phrase refers to brightness, it does not. The sun remains an extraordinary object in the sky despite losing the feature that makes it obviously solar. A distant observer could no longer rely on visible width alone to recognize it as a nearby stellar surface. Instead, brightness would become the clue. The point would be too intense. It would stand apart from the surrounding stars not because it looked larger, but because it delivered far more light. This shift changes the character of the journey. Earlier, from Mars to Jupiter, both the disk and the brightness still carried an unmistakable sense of proximity. At Neptune. The disk approached the edge of naked eye resolution. In the Kuiper Belt, that edge has effectively been crossed for ordinary vision. The sun is now entering a regime where shape has almost finished its transformation, while brightness has barely begun to approach the range associated with normal stars. The result is not a gradual fading into anonymity, but a long intermediate phase in which the sun is visually compact and still overwhelmingly conspicuous. Distance keeps increasing, and the angular diameter keeps falling in simple proportion. At 50 astronomical units, the disk is only about 1/50th as wide as from Earth. No sudden event occurs there. The sun does not flicker into a point at a precise boundary. Human eyesight has no perfectly sharp threshold, and optical resolution depends on conditions and instruments. What matters is the scale. By this stage, the solar face has become too small to carry the intuitive identity it has in the terrestrial sky. Sunspots, granulation, and the visible texture of the photosphere require telescopic observation. The unaided eye is left with brightness rather than structure. That is exactly how distant stars are normally experienced. But with one major exception, the sun is still much too luminous in apparent terms. The surrounding stars would remain essentially unchanged during this part of the outward journey. Their distances are so enormous that moving a few dozen astronomical units barely alters their apparent brightness or positions for ordinary visual purposes. The sun, by contrast, is changing rapidly because the observer is still close enough for each additional astronomical unit to matter. This creates an unusual sky in which one point is fading noticeably with travel, while the rest of the stellar background remains almost fixed. The sun is gradually joining a pattern that was already there, but it has not yet reached the level required to disappear into it. Even the architecture of the solar system begins to compress from this distance. The giant planets lie closer to the sun's apparent position than they do from Earth, and the inner planets are packed into an even smaller region around the central glare. The entire planetary system is beginning to occupy a narrow patch of sky, though it is still far from appearing as a single unresolved source to capable instruments. The sun remains the obvious anchor because its light dominates everything nearby. This gradual compression hints at what will happen much farther away, when the planets become increasingly difficult to separate and the whole system starts to resemble the remote stellar systems observed from Earth. Yet the Kuiper Belt is still a local neighbourhood by galactic standards. Its most important lesson is therefore not how distant the sun has become, but how close a star must be for its brightness to remain exceptional after its disk is gone. The familiar circle has nearly vanished from ordinary sight. The light is weakened by factors of thousands. The environment has become cold, dark, and remote compared with Earth. Still, the sun refuses to behave like an ordinary star. Its shape has crossed one threshold, but its brightness remains on the wrong side of another, leaving a long stretch of distance in which the observer sees something that looks stellar without yet belonging to the stellar background. At 100 astronomical units, the sun has crossed a visual threshold that once seemed far more important than it actually turns out to be. Its apparent diameter is now only about 18 arcseconds, far below the scale at which unaided human vision can recognize a circular disk. The photosphere still exists with the same enormous physical width, but from this distance, it has been compressed into a source that is effectively stellar in shape. No ordinary glance could recover the broad solar face familiar from Earth. There would be no obvious edge, no sense of a glowing circle hanging in the sky, and no visible surface structure without optical aid. In that limited sense, the transformation is complete. The sun looks like a star, yet almost everything about its brightness still argues that it is not an ordinary one. At 100 astronomical units, its apparent visual magnitude is roughly -16.7. That is vastly dimmer than the sun appears from Earth. but it remains overwhelmingly brighter than Venus. Sirius, or any normal star seen in the terrestrial night. The difference exposes just how misleading appearance can become. Once angular size has fallen below the limits of vision, a point of light can be extraordinarily intense. The Sun has lost its visible disk long before it has lost its dominance. This is the stage where the two journeys, one in apparent size and one in apparent brightness, have separated completely. Geometrically, the Sun has already entered the stellar regime. Photometrically, it is still far outside it. The distance of 100 astronomical units is roughly twice the outer edge of the classical Kuiper Belt, placing the observer beyond most of the region where the familiar population of Kuiper Belt objects is concentrated. The major planets now occupy a small angular region around the Sun. Their enormous orbital separations, which dominate navigation from within the solar system, have begun to compress from the viewpoint of a distant observer. Neptune's orbit, despite spanning billions of kilometers, it is no longer a grand circle across the sky, but part of a comparatively narrow central structure. The farther outward the observer moves, the more the architecture of the solar system changes from an environment into an object. This is a quiet but profound shift in perspective. Within the planetary system, the Sun sits at the center of a huge arrangement of worlds spread across vast distances. From far outside, those same distances begin to collapse into angular proximity, and the Sun becomes the brightest point within an increasingly compact family. Even so, the system has not yet become truly star-like. As a whole, instruments could still separate planets from the Sun under favorable geometry, and the Sun's brightness would make observation of nearby faint objects difficult. What has changed most clearly is the disappearance of the solar disk to unaided vision. At 18 arcseconds, the source is far smaller than the normal resolving capacity of the human eye. A telescope can enlarge the image, but the naked eye receives only a concentrated point. That point, however, would be extraordinarily conspicuous. The inverse square law has reduced the solar energy by a factor of roughly 10,000 compared with Earth, because the distance has increased by a factor of 100. This sounds like the kind of reduction that should finally make the Sun weak, and in physical terms the change is severe. Solar heating is only a tiny fraction of what it is near Earth. A surface exposed to sunlight would remain extremely cold compared with the inner planets. Solar power systems would struggle to collect useful energy without very large areas. The warmth associated with sunlight would be almost absent from human intuition, yet visible brightness and thermal significance are not judged against the same reference. The Sun at Earth begins so bright that removing more than 99.9% of its received energy still leaves a source far beyond the normal stellar range. The point in the sky remains intense even while its ability to warm distant objects has become weak. This contrast is one of the most useful ways to understand the outer solar system. It is possible to stand in a region that is thermally dominated by cold and still see a sun that is visually brilliant. Darkness in space is not a simple measure of how much solar energy exists. A black sky can surround a bright source because there is almost nothing between source and observer to scatter the light. The Sun itself can remain piercing while nearby space looks empty. At 100 astronomical units, that effect would be especially clear. The stellar background would remain largely unchanged. Constellations would look almost as they do from Earth, because even a displacement of 100 astronomical units is tiny compared with the distances to the stars. The Sun, however, would have changed dramatically because the journey began close to it. Against an almost familiar pattern of distant stars, one point would stand out with an intensity that betrayed its proximity. The paradox is visual rather than physical. Everything about the Sun's shape now resembles the stars, but its brightness reveals that it still belongs to the local environment. The observer has travelled far enough to lose the disk, yet not far enough to lose the privilege of being near one particular star. This is also a useful distance for thinking about what the word near means in astronomy. 100 astronomical units is enormous, compared with the scale of Earth's orbit, and far beyond the major planets. Spacecraft require years to decades to reach such regions. In human travel terms, it is almost unimaginably remote. In stellar terms, it is still intimate. Interstellar distances are measured not in hundreds of astronomical units, but in hundreds of thousands. The nearest neighbouring star systems remain vastly farther away than the Sun is from an observer at 100 astronomical units. The Sun therefore continues to behave like a nearby source even after the planetary system has started to recede behind the observer. This explains why the brightness remains so extreme. Distance has erased spatial detail without yet erasing luminous dominance. The progression also reveals why there is no single moment when the Sun becomes another star. At 100 astronomical units, one reasonable criterion has already been satisfied. It is point-like. Another has not come close. It is still much brighter than any star normally seen from Earth. If appearance is defined only by angular resolution, the answer could already have arrived somewhere in the outer solar system. If appearance includes brightness, the journey must continue by orders of magnitude. The next distances are no longer simply extensions of planetary travel. They lead toward the vast, uncertain region associated with the Oort Cloud, where the Sun continues fading while the architecture of the known planetary system collapses into a tighter central patch. At 100 astronomical units, the Sun has surrendered its face, but not its identity. Its width is gone to the naked eye. Its light is diminished by a factor that sounds enormous. Yet the point that remains is still too brilliant to belong naturally among the stars. The darkness has grown, but it has not won. At 1,000 astronomical units, the solar system no longer feels like a collection of neighbouring worlds spread around an observer. It begins to feel like something being left behind. The known planets occupy a tightly compressed region near the Sun's position. The broad architecture of their orbits has contracted into small angles, and the Sun itself has become an unresolved point beyond any possibility of naked-eye disk recognition. Yet this point still refuses to behave like an ordinary star. Its apparent visual magnitude is roughly minus 11.7, placing it in the same general brightness realm as the full moon seen from Earth. Though somewhat fainter, the comparison is revealing because the two objects would look completely different. A full moon spreads its light across a broad disk about half a degree wide, while the Sun, at 1,000 astronomical units, concentrates its light into a point too small for unaided vision to resolve. The total apparent brightness can be discussed on a similar magnitude scale, but the visual experience would not be similar. One is an extended luminous surface in the night sky. The other is an intense, needle-like source embedded in darkness. This is how far the journey has already changed the meaning of sunlight. Near Earth, the Sun is both large and overwhelmingly bright. Near Neptune, it becomes tiny while remaining extremely bright. At 1,000 astronomical units, even the idea of a visible solar face has become irrelevant without telescopic magnification. Yet the light concentrated into that point still exceeds the brightness of every normal star by an enormous margin. The observer has moved 10 times farther from the Sun than at 100 astronomical units, so the received solar energy has fallen by another factor of 100. Compared with Earth, the energy per unit area is now reduced by roughly a factor of 1 million. Solar heating has become extraordinarily weak. A small body drifting in this region receives so little sunlight that its thermal environment is governed by deep cold, internal properties, and the faint background of space far more than by anything resembling terrestrial warmth. Still, the apparent brightness of the Sun demonstrates how different visual perception can be from thermal significance. A source can deliver only a millionth of the solar energy received at Earth and remain brilliant enough to dominate the sky. That apparent contradiction exists because human eyes are extraordinarily sensitive to light, and because the Sun begins the journey from an almost absurdly bright starting point. The distance of 1,000 astronomical units also brings the observer toward a region where the structure of the solar system becomes much less certain. The planets and the Kuiper Belt are mapped as populations with directly observed members. The Oort Cloud is different. It is inferred as a vast, distant reservoir of icy bodies that can supply long-period comets, and its exact boundaries are not directly observed in the same way as the planetary orbits. Estimates often place its inner regions at distances of several thousand astronomical units, with possible extensions vastly farther outward. 1,000 astronomical units, therefore, does not mark a clean entrance through a physical wall. There is no visible shell announcing that the Oort Cloud has begun. Instead, it represents an approach to the immense transition zone where the familiar flattened structure of much of the planetary system gives way to a more distant and potentially much more spherical population of small bodies. The uncertainty itself is significant. Close to the Sun, orbital architecture is traced through planets. Moons, asteroids, and observed trans-Neptunian objects. Farther out, the inventory becomes increasingly incomplete. The Sun remains easy to locate because it is still so bright, but much of the material gravitationally associated with it may be extraordinarily difficult to see. A distant, icy body reflects only a tiny fraction of already weakened sunlight, and that reflected light must then cross the distance back toward an observer. Objects can therefore remain almost invisible even while the Sun that governs their broad orbital environment is glaringly obvious. This creates a strange reversal of the inner solar system. Near Earth, planets and moons can be prominent, while distant small bodies are difficult to notice. At 1,000 astronomical units, the central star remains obvious, yet the system around it becomes increasingly hidden. The planets themselves are now packed very close to the Sun in apparent angle. Earth's orbital radius, once the reference scale for measuring the solar system, spans only a tiny fraction of the sky from this distance. Even Neptune's vast orbit occupies a much narrower angular extent than it does from anywhere within the planetary region. To unaided vision, there would be no recognizable diagram of planets arranged around a central sun. The familiar solar system has collapsed almost into a direction. Sophisticated instruments could still separate individual worlds under favorable circumstances, but the observer is approaching the perspective from which planetary systems begin to resemble the distant systems studied around other stars. This compression carries an important consequence. The Sun is becoming star-like, not only as an isolated source, but as the center of a system whose internal spacing is disappearing from ordinary view. The transformation is therefore broader than the fading of one object. It is the conversion of an inhabited astronomical environment into a remote-looking system. From within, each planet has its own sky, orbit, seasons, and physical presence. From far enough away, those differences are compressed into subtle motions and faint points clustered around a star. At 1,000 astronomical units, that process has clearly begun. Although the observer is still vastly closer to the Sun than to any neighbouring star, this is the scale mismatch that continues to define the journey. 1,000 astronomical units is 10 times farther than the distance used for the previous milestone and immensely beyond the major planets. But even this is only a small fraction of a light year. Interstellar space remains ahead on a scale that makes the voyage so far seem almost local. The Sun's brightness confirms that. A normal bright star viewed from Earth does not illuminate the landscape like the Moon. It contributes almost nothing to ordinary surface lighting. The Sun, at 1,000 astronomical units, is already deprived of nearly all its terrestrial heating power. Yet as an apparent point source, it remains comparable in magnitude to one of the brightest extended objects in Earth's night sky. It could still cast perceptible shadows under suitable conditions because its light remains highly directional and concentrated. Although the exact appearance would depend on the surface and surrounding environment, there would be no broad daylight created by atmospheric scattering unless an atmosphere were present to redirect that weakened light. But the source itself would remain unmistakable. The black sky around it would be filled with stars whose appearance had barely changed from the patterns known near Earth, while one point among them shone with a brightness entirely out of proportion to the rest. That point would reveal the observer's true location. The disk might be gone, the planets might be compressed, and the warmth might be nearly absent, but the observer would still be gravitationally and visually close to one particular star. The Sun has not yet become anonymous. The next great reduction in brightness requires another enormous increase in distance. Moving outward by a factor of 10, once again, will cut the received light by another factor of 100, pushing the Sun toward an apparent brightness that begins to resemble the most brilliant objects of a terrestrial night sky rather than the Moon. Only then does the description of an extremely bright star start to feel visually natural. At 1,000 astronomical units, that transition is approaching, but it has not arrived. The solar system has contracted behind the observer. The solar disk has vanished completely into a point, and the warmth of sunlight has almost disappeared. Yet the point itself still shines too strongly to surrender its local identity. At 10,000 astronomical units, the Sun has finally entered a range where the phrase extremely bright star begins to describe its appearance more naturally than the word sun. The observer is now deep within the immense distances associated with the predicted Oort Cloud, a region so remote that even its broad structure is reconstructed indirectly from the behavior of long-period comets rather than mapped as a complete population. From this distance, the Sun is still the same star physically, but almost every familiar visual clue has been stripped away. Its disk is far below naked eye resolution. Its apparent position gathers the major planets into an exceedingly tight region. Its light no longer produces anything resembling terrestrial daylight, unless some atmosphere or surface is available to scatter and reflect it. What remains is a concentrated point whose apparent visual magnitude is roughly -6.7. That is still brighter than Venus at its most brilliant as seen from Earth. The Sun has therefore not yet become an ordinary star, but for the first time it belongs to a visual category that feels recognizably stellar. It is a point in a dark sky, extraordinarily bright but no longer moon-like in total apparent intensity, and no longer connected to any visible circular surface. The transition matters because this is the first stage where brightness itself has begun to approach the familiar range of nighttime celestial objects. At 1,000 astronomical units, the Sun was still comparable in overall brightness to the full moon. At 10,000 astronomical units, another factor of 10 in distance has reduced the received light by another factor of 100. The inverse square law continues to operate without interruption, but perception changes categories. As the numbers cross familiar benchmarks, a point brighter than Venus is still striking, yet it can be understood as something star-like rather than as a displaced version of daylight. This is not because Venus and the Sun are physically comparable. Venus shines by reflected sunlight, while the Sun generates its own energy through nuclear fusion. The comparison is purely about apparent brightness from a particular location. That distinction is useful because apparent magnitude says nothing by itself about what an object is. It records how bright the source looks. A nearby planet, a distant star, and the Sun viewed from far away can occupy similar parts of the magnitude scale while having completely different physical origins. At 10,000 astronomical units, the Sun begins to enter the same observational language that is normally used for the brightest points of the night sky. The geometry of the solar system has also changed almost beyond recognition. From this distance, Earth's orbit is compressed into an angle so small that the entire inner planetary system sits extremely close to the Sun's position. Even Neptune, whose orbit defines the broad scale of the major planetary system, is gathered into a narrow patch around the central point. To unaided vision, there is no planetary arrangement spread across the sky. There is only a brilliant source surrounded by stars. With the hidden architecture of planets reduced to motions and separations that instruments would have to extract from the glare, the observer is beginning to see the solar system in the same general way distant planetary systems are studied from Earth. The star is obvious. The planets are difficult. Their reflected light is faint. Their angular separation from the star is small, and their brightness is suppressed by the enormous contrast between them and the central source. This reversal is important because the journey has crossed from living inside the system to viewing it more like an external object. The Sun no longer defines a broad visual environment, it defines a location. The planetary system has become something clustered around that location rather than something extending around the observer. The Oort Cloud adds another layer of scale. Estimates of its outer extent can reach toward roughly 100,000 astronomical units, meaning that 10,000 astronomical units may still lie well within the Sun's distant gravitational domain. There is no known bright boundary to cross and no visible wall of icy bodies. The region is expected to be sparse. Individual objects would be separated by enormous distances, and most would be extremely difficult to detect because sunlight has become so weak. A body at this distance receives only a tiny fraction of the solar energy available at Earth, and whatever light it reflects must travel outward again before reaching an observer. The Sun can remain a conspicuous point, while the material loosely associated with it becomes almost completely hidden. The system therefore grows less visible even as its true spatial extent grows larger. That contrast is one of the quietest forms of astronomical scale. What belongs to the solar system is no longer defined by what can easily be seen, but by gravity, orbital history, and the long influence of the Sun across regions where its light has become faint. The Sun's gravitational reach does not fade according to the needs of human vision. An icy body can remain weakly bound over immense intervals even when the Sun looks only like an unusually bright star. The same distance also changes the practical meaning of warmth. At 10,000 astronomical units, direct solar heating is negligible compared with the conditions familiar near the planets. The energy flux has fallen by a factor of roughly 100 million compared with Earth. An object there exists in an environment close to the deep cold of interstellar space, with the sun contributing very little thermal comfort despite still being obvious to the eye. This is another reminder that visual brightness can be deceptive. A point can appear brilliant while delivering very little total energy to a surface, because the eye can respond to extraordinarily small amounts of visible light. The sun is no longer an environmental presence in the terrestrial sense. It is a beacon. Its position still identifies the center of the system, but its heat no longer makes the surrounding region feel solar. The darkness has changed character as well. Earlier in the journey, darkness surrounded a source that still carried the visual authority of a nearby sun. Here, the dark sky has become the primary setting, and the solar point sits within it rather than dominating it conceptually. The distant stars remain almost unchanged because moving 10,000 astronomical units is still small compared with their typical distances. Though the shift is now large enough that stellar parallax and perspective differences become more meaningful than they were within the planetary system. The sun is beginning to take its place against a background whose geometry is no longer perfectly identical to the one seen from Earth. Even so, the observer remains much closer to the sun than to the nearest neighbouring stars. 10,000 astronomical units is still only a fraction of a light year. This is why the sun remains so bright. Interstellar distance has not fully arrived. The journey has entered the outermost architecture of the solar system without yet reaching the distance required for the sun to blend into the ordinary stellar population. That blend will demand another enormous expansion in scale. The important change here is psychological only in the sense that visual categories have shifted. There is no disk left to suggest a solar surface. There is no daylight halo in empty space. There is no planetary spread broad enough for unaided vision to read as a system. There is simply a luminous point, brighter than the brightest planets seen from Earth, occupying one position among countless other points. If its identity were not already known, appearance alone would reveal very little about its special relationship to Earth. The sun has become something that looks like an exceptional star, rather than something that looks like a sun. Yet exceptional is the word that still prevents the transformation from being complete. Its brightness remains too high to disappear comfortably into the stellar background. The observer must move outward through the rest of the sun's distant gravitational territory before even that remaining distinction begins to weaken. At 10,000 astronomical units, the familiar sun is gone from sight, but a brilliant star still marks the way back. Near the outer reaches of the sun's distant gravitational domain, the most important change is no longer the disappearance of the solar disk. That happened long ago. The deeper change is that the solar system itself is beginning to disappear as a place. Across distances that may approach 100,000 astronomical units, in the broad outer territory often associated with the Oort Cloud, the planets no longer seem distributed through a vast architecture surrounding the observer. Their separations collapse into tiny angles around the sun, and the familiar scale of the planetary system is compressed into a compact patch of sky. Earth, Mars, Jupiter, Saturn, Uranus, and Neptune still occupy enormous physical orbits, but distance has changed the way those orbits are projected. From far enough away, even billions of kilometers become visually small. The solar system is not shrinking in any physical sense. It is being reduced by perspective into the form that distant planetary systems have always presented to astronomy: one dominant star, surrounded by much fainter companions that are difficult to separate from its light. The outer Oort cloud does not have a known sharp edge. It is expected to be a sparse and extended population rather than a shell with a visible boundary, and estimates of its reach remain uncertain. Some models place its outer regions at distances that represent a significant fraction of the journey to the nearest neighbouring stars. In that immense transition zone, the sun's gravity competes increasingly with the tidal influence of the Milky Way and with passing stars. Objects can remain loosely associated with the solar system, yet their orbits are fragile enough to be altered over long intervals by forces that are almost irrelevant to the planets. The solar system therefore fades outward, not through a wall but through weakening dominance. Close to the sun, its gravity overwhelmingly controls planetary motion. Farther away, that control becomes less exclusive. By the time the observer approaches the most distant plausible reaches of the Oort cloud, the distinction between belonging to the solar system and moving through the surrounding galactic environment has become less visually obvious and more dynamically subtle. The sky provides little help. The sun is only a point. The planets are crowded so tightly around it in apparent position that unaided vision cannot separate them. Even the enormous orbit of Neptune spans only a very small angle when seen from these distances. The inner planets lie closer still, buried near the solar point and overwhelmed by the contrast in brightness. What once required years of spacecraft travel to cross is now compressed into a region that can be covered by a small instrument field. The scale of the transformation is easier to understand by reversing the problem. From Earth. Exoplanets are usually difficult to see directly because they lie extremely close to their host stars in angular terms while being vastly fainter. The difficulty is not that the planets are physically close to the stars in every case. It is that their systems are so distant that wide orbital separations project into tiny angles. The solar system, viewed from its own far outskirts, begins to enter the same geometry. Its planets become faint companions beside a dominant stellar point. Their individual identities have not vanished, but direct visual access to them has become a problem of contrast and resolution rather than simple eyesight. Earth becomes especially anonymous. From within its orbit, the planet is a world with continents, oceans, clouds, and a moon. From the far Oort Cloud, it is a tiny reflector of sunlight, extremely close to the sun in apparent angle and far too faint to command attention. Nothing visible at a glance announces that one of those hidden points carries liquid oceans or a biosphere. The same is true of Jupiter's storms, Saturn's rings, the ice giants, and the smaller worlds beyond them. Their physical richness survives while their apparent separateness collapses. The observer has reached a distance where the solar system's complexity is no longer obvious from its appearance. This is a critical step towards seeing the sun as just another star, because a star is never observed in isolation from the question of what may surround it. From Earth, most stars look solitary, even when they possess planets. Debris disks, companions, or distant reservoirs of small bodies. Their systems are compressed by distance into the light of the central star. Near the outer edge of the solar system, the sun begins to acquire that same disguise. It is still brighter than an ordinary star would appear from Earth, but the system around it is becoming visually hidden in precisely the way other planetary systems are hidden from us. The sun is no longer a broad centre with visibly separated worlds spread across a sky. It is a point with an unresolved family. That compression also changes the meaning of direction. Deep inside the solar system, the difference between inward and outward is obvious because the sun dominates one side of the sky and planetary distances remain part of the surrounding environment. Far away, the entire known planetary system lies nearly along the same line of sight. Looking back toward the sun means looking toward almost everything that once defined the local astronomical landscape. The planets, asteroids, Kuiper Belt objects, and the region of Earth's orbit all occupy a narrow cone, centered on a star-like point. Looking away means facing the wider galaxy, where neighboring stars begin to matter more as destinations and gravitational influences than they did inside the planetary system. The observer is approaching a genuine change of context. The solar system has stopped filling space and has started occupying a direction within space. The Oort Cloud, if its most distant members extend as far as predicted, makes this transition gradual. An observer could still be among objects that are weakly bound to the sun, while already seeing the planetary system as a compact stellar source. This is a reminder that visual appearance and gravitational membership are not the same thing. A body may belong dynamically to the solar system even when the sun looks almost indistinguishable in form from other stars. The sun's identity is carried not by visible width but by brightness. Known position, motion, and gravitational influence. Far from the planets. Those become the clues that matter. Even the sun's brightness is now approaching a more familiar stellar range as the journey continues outward. The enormous reductions accumulated since Earth have removed the daylight character entirely. There is no broad solar disk, no surrounding blue sky in empty space, and no visible planetary arrangement that immediately identifies a home system. Instead, there is a bright point against a field of other points, with the main difference still lying in how conspicuous that point remains. This is where the idea of losing the sun becomes more precise. The sun has not disappeared, and it has not become physically less important to the objects still bound to it. What has been lost is the visual evidence that this point is the center of an elaborate planetary environment. That evidence has collapsed below ordinary resolution. From here, the solar system begins to resemble the distant systems that telescopes detect through indirect clues, tiny changes in stellar motion, faint reductions in light during transits, or weak planetary photons separated from overwhelming stellar glare. The observer is still inside the sun's extended domain, yet the view has already become external in character. This inversion is one of the quietest milestones in the entire journey. The sun first lost its apparent size, then it lost much of its thermal authority. Now, the system around it is losing its visible structure. Beyond this region, distance will begin, changing the remaining distinction that matters most, the sun's brightness relative to the stars. Once the voyage is measured naturally in light years rather than astronomical units, the local star will no longer merely look point-like. It will begin to fall into the same brightness hierarchy as Sirius, Vega, and the other bright stars of a dark sky. Near the solar system's outer reaches, that final transformation is still incomplete, but the stage is prepared. Behind the observer, an entire planetary system has contracted toward a single light. 1 light-year from the sun sounds like a distance that should be enough to make it ordinary. It is already far beyond the outer planets, far beyond the Kuiper Belt, and far beyond the distances normally used to describe even the more remote reaches of the solar system. A light-year is the distance light travels through vacuum in 1 year, and measured in astronomical units, it is a little more than 63,000 times the average Earth-Sun distance. By the time an observer has reached such a separation, the familiar planetary system has collapsed into an extremely compact region around the Sun. The solar disk has long since vanished below naked eye resolution, and almost every physical reminder of proximity has been stripped away. Yet one feature remains unexpectedly persistent. The Sun is still bright, at a distance of 1 light-year. Its apparent visual magnitude is roughly -2.7. That places it well within the range of the most conspicuous objects in a dark sky. More importantly, it would still appear brighter than Sirius does from Earth. Sirius, the brightest star in the terrestrial night sky, has an apparent visual magnitude of about -1.5. The difference may seem modest when written as magnitudes, but the scale is logarithmic, so even a change of a little more than 1 magnitude represents a substantial difference in apparent brightness. The result is quietly counterintuitive. Travelling an entire light-year away from the Sun still does not reduce it to the level of an ordinary bright star. It remains exceptional. This is the first stage of the journey where interstellar distance has truly begun. Yet the Sun still carries the unmistakable signature of being comparatively nearby. Its brightness reveals what its shape no longer can. To the eye, the Sun is now just a point, but it is a point that outshines every star in the familiar Earth sky. That makes 1 light-year an important test of scale because it exposes how inadequate ordinary intuition is for judging the distances between stars. The solar system is enormous when measured against human travel. The outer planets are remote. The Kuiper Belt is broader still, and the predicted Oort Cloud may extend to distances that seem almost unimaginable when expressed in kilometers. But neighboring stars are farther away by another immense step. 1 light-year is large enough to escape the planetary architecture and yet still too small to place the Sun comfortably into the stellar background. This happens because brightness declines continuously rather than categorically. The inverse square law keeps reducing the sunlight as distance grows. But there is no special rule that activates once the observer crosses from a region called the solar system into a region called interstellar space. The Sun simply continues fading according to the same geometry it followed near Neptune, in the Kuiper Belt, and across the Oort Cloud. At 1 light-year, the accumulated reduction is enormous. The energy per unit area is only a minute fraction of what reaches Earth. Solar heating has become negligible for anything resembling terrestrial conditions. The Sun no longer behaves as a meaningful source of warmth in the everyday sense. It remains visible because eyes are sensitive to extraordinarily low levels of light, not because the observer is still living in anything like the illuminated environment of the inner solar system. That separation between visibility and influence is now nearly complete. The Sun can appear brilliant as a point while contributing almost nothing to the thermal character of the surrounding space. It has become a visual marker rather than an environmental presence. The rest of the sky would also begin to feel less familiar. At smaller distances within the solar system, the stars remain almost fixed because the observer's movement is tiny compared with their distances. A displacement of 1 light-year is no longer tiny in the same way. It is still smaller than the distance to the nearest neighbouring stellar system, but large enough that the apparent positions of nearby stars begin to shift noticeably relative to more distant ones. Constellations are not permanent drawings attached to a sphere. They are perspective patterns created from stars at very different distances. Moving through interstellar space changes the viewing geometry, and after a journey of 1 light-year, some of those patterns would already begin to distort. The Sun would join that changing field as one of the brightest points, but unlike the distant background stars, it would be the one object whose fading had been followed continuously from disk to point. That continuity gives the observer knowledge that appearance alone no longer provides. Nothing in the shape of the Sun would reveal oceans, continents, or inhabited planets around it. Earth would lie far too close to the solar point in angular separation for unaided vision, and its reflected light would be overwhelmed. The entire history of the inner solar system would be hidden inside the glare of what looks like a single bright star. This is almost exactly the observational problem encountered when astronomers study planetary systems elsewhere. A star can be easy to detect while its planets are extremely difficult to separate. Brightness, contrast, and angular separation work together to hide the smaller bodies. From 1 light-year away, the solar system has become a powerful example of that problem. Earth does not vanish physically. It vanishes observationally into the vicinity of the Sun. Jupiter still circles on its wide orbit. Saturn still carries its rings. Neptune still moves slowly through the outer planetary dark. Yet from this perspective, those differences are reduced to tiny structures around a single point of light. The Sun, therefore, becomes more star-like, not merely because of its own appearance, but because everything surrounding it becomes hidden in the way planetary systems around other stars are hidden from Earth. The remaining obstacle to ordinariness is brightness. A magnitude near -2.7 would make the Sun one of the dominant points in any dark sky. It would immediately attract attention. An observer without prior knowledge might reasonably classify it as an unusually bright nearby star. That description would be correct. The only misleading part would be to call it ordinary. Even at this distance, the Sun has not faded enough to blend naturally with the rest of the stellar population. This matters because the phrase, "just another star," can mean more than point-like shape. A point can still be exceptional. A star can still dominate its neighbourhood of sky. If ordinariness means that the Sun no longer attracts immediate visual attention, then 1 light-year is not enough. The distance must increase further until its apparent magnitude falls toward the range occupied by the brightest familiar stars. The comparison with Sirius makes that threshold concrete. Sirius is already a striking object from Earth. It is the brightest star in the night sky, clearly more prominent than most of its neighbours. If the Sun at 1 light-year is still brighter than Sirius, then the observer has not yet reached a place where the Sun could plausibly disappear into the general pattern. It has become stellar, but not anonymous. This is a useful distinction because the entire journey has repeatedly crossed thresholds that seemed at first like final answers. Near Neptune, the disk became so small that the Sun approached a point. In the Kuiper Belt, its shape became effectively stellar to unaided vision. Farther out, its total brightness fell from solar levels toward those of familiar nighttime objects. Near the distant edges of the solar system, the planetary architecture itself collapsed into a compact stellar-looking system. Yet at 1 light-year, another supposed final boundary fails. Interstellar space has arrived, but ordinary stellar brightness has not. The Sun remains too conspicuous. The next meaningful milestone, therefore, lies not at a named physical border, but at a brightness comparison. The question becomes how far the observer must move before the Sun fades to something like Sirius. That distance is only modestly farther in light-year terms. But conceptually it marks a deeper change than crossing the outer solar system. Once the Sun reaches that level, it will no longer be an overwhelmingly dominant point. It will finally occupy the same broad visual category as the brightest stars already known from Earth. 1 light-year is therefore a threshold of disappointment only if distance is expected to work faster than it does. The Sun has lost its disk, its warmth, its visible planets, and its environmental authority. Almost everything that made it feel like the sun is gone. Still, the point left behind shines with enough intensity to reveal that the journey has not gone far enough. Even across 1 light-year of darkness, the local star is still special, around 1.8 light-years from the sun. The comparison finally shifts in a meaningful way. The solar point that remained brighter than Sirius at 1 light-year has now faded to roughly the brightness Sirius shows from Earth. Placing the sun inside a visual category that has been familiar all along, it is still bright. It would still attract attention in a dark sky, but it is no longer so bright that it clearly belongs to a different class from every ordinary star. For the first time in the outward journey, the sun can be described not merely as point-like, but as resembling one of the brightest stars normally seen from Earth. This threshold does not correspond to any wall in space, any edge of a gravitational region, or any sudden change in the physical state of the sun. It emerges entirely from apparent brightness. The star itself continues producing energy as before. Only the amount of that light reaching the observer has fallen far enough for comparison with Sirius to become natural. This makes the distance more conceptually important than many of the physical boundaries crossed earlier. The Kuiper Belt mattered because the solar disk became difficult to resolve. The distant Oort Cloud mattered because the architecture of the solar system began collapsing into a compact source. 1 light-year mattered because the observer was clearly in interstellar space, while the sun still remained unexpectedly brilliant. Around 1.8 light-years. However, the last obvious visual sign of exceptional proximity begins to soften. The sun now behaves in the sky the way a very bright star behaves. It is an unresolved point. It is surrounded by blackness. It no longer provides meaningful warmth. Its planets are hidden near its position, and its apparent magnitude has fallen into a range that belongs to the stellar night, rather than to the overwhelming brightness levels associated with the solar system's inner regions. Sirius provides an especially useful comparison because it is not an ordinary faint star. It is the brightest star in Earth's night sky. Reaching Sirius-like brightness, therefore, does not make the sun inconspicuous. It establishes something subtler. The sun has become visually plausible as a star among stars. An observer who did not know its history would have no reason to infer from shape alone that this point had once occupied half a degree of sky, warmed oceans, illuminated continents, and defined the day side of a living planet. Those facts belong to distance and context, not to the point of light itself. Seen from 1.8 light-years away, the sun carries no visible memory of having been a sun in the familiar human sense. It is simply a luminous stellar source. The transformation reveals how strongly astronomical identity depends on location. From Earth, Sirius looks like a brilliant point because it is far away, while the sun looks like a disk because it is close. Move away from the sun, and that distinction eventually disappears. Both become points. Their brightnesses can even enter the same range. The physical difference between them has not vanished, but the visual difference that once seemed fundamental has been reduced to stellar details such as color, spectrum, luminosity, and motion. The sun no longer announces itself through sheer dominance. To identify it confidently, an observer would need information beyond naked eye appearance. Its spectrum would reveal the absorption features of a warm main-sequence star. Precise astrometry could reveal its position and motion. Instruments sensitive enough to separate faint nearby companions might search for evidence of planets. None of those clues, however, would restore the emotional category created by proximity. The solar point would remain a star in the sky, not a broad source filling the visual and physical environment. This is also where the idea of home becomes observationally fragile. Earth still exists at the same orbital distance from the sun, but from nearly 2 light-years away, the planet is hidden overwhelmingly close to the star in angular terms. Its reflected light is vastly weaker. The entire inner solar system is compressed into a region that unaided vision cannot disentangle. The distinction between a star with an inhabited world and a star without one is therefore invisible at a glance. Nothing in the brightness of the sun itself discloses the presence of oceans, forests, cities, or biology. The point looks important only because it is bright, and at this stage even that importance is no longer unique. A sky already filled with stars can accommodate an object like this without being transformed by it. That marks a sharp contrast with Earth, where the sun determines whether the sky is day or night and controls the visibility of almost everything else. Around 1.8 light-years away, the Sun has no such authority. Other stars remain visible around it. The galactic background remains present. There is no solar glare spread through an atmosphere unless the observer happens to stand within one. And even then, the weakened light would not create anything resembling terrestrial daylight. The Sun has become part of the sky rather than the condition that determines the sky. The surrounding constellations would also have changed more noticeably by this distance. A displacement approaching 2 light-years is large enough to alter the perspective on nearby stars. Since the familiar constellations are only accidental projections of three-dimensional stellar positions, some stars would shift against more distant backgrounds, and familiar patterns would begin to loosen. Within that rearranged stellar field, the Sun would occupy a new location as another nearby star. It would be unusual only because the observer knows where it came from. The visual field itself offers no label distinguishing it from the rest. This is one of the quietest reversals in the entire journey. Near Earth, every other star is background, and the Sun is the central source. Near 2 light-years away, the Sun has entered the background. It has not become faint, but it has become comparable. That difference matters more than the absolute number attached to the distance. A star that once erased Sirius from the daytime sky has now fallen until Sirius becomes the appropriate reference. The hierarchy has changed from absolute domination to membership in the same broad brightness class. Even here, however, the Sun is not yet ordinary in the strongest sense. Sirius itself is exceptional. It is brighter than every other star in Earth's night sky. So matching its apparent brightness means that the Sun would still stand out strongly. The transition at 1.8 light-years, therefore, represents a first stellar normalization rather than full anonymity. The Sun has entered the realm of very bright stars, not the broad population of modest ones. To become genuinely easy to overlook, it must continue fading across several more light-years. This distinction prevents the journey from ending too early. The title asks when the Sun becomes just another star. But another star can mean several things. If it means a point rather than a disk, that happened in the outer solar system. If it means an object with brightness comparable to a familiar bright star, then the answer lies around this distance. If it means a star that no longer seems unusually luminous in the sky, the observer must move farther. Each interpretation captures a different stage of the same continuous transformation, around 1.8 light-years. The brightness threshold is especially compelling because it removes the last enormous gulf between the Sun and the brightest stellar points known from Earth. The observer has finally travelled far enough that the Sun can be placed naturally alongside Sirius rather than alongside the Moon, Venus, or the daylight Sun itself. Yet the next step will change the comparison again. Beyond this distance lies the neighbourhood of Alpha Centauri, where the Sun's apparent brightness falls still further and where the view becomes the reverse of the one known from Earth. From there, the nearest familiar stellar system would look back and see the Sun not as a privileged beacon but as a bright, ordinary member of its own night sky. Around 1.8 light-years, that outcome is no longer theoretical in appearance. The Sun has already become a star. What remains is for it to become less remarkable. From the neighbourhood of Alpha Centauri, the Sun finally enters a sky in which it can no longer claim any obvious visual privilege. The Alpha Centauri system lies about 4.4 light-years from the Sun, and from roughly that distance, the solar point would shine at an apparent visual magnitude near plus 0.4. That is still bright enough to be noticed easily under a dark sky. It would not be a faint object, and it would not vanish into the background, but it would no longer dominate the field in the way it did from 1 light-year away, and it would no longer resemble the special category of source that defined the earlier stages of the journey. It would look like a bright star. Nothing in its naked eye form would reveal that this point is the same object that appears half a degree wide from Earth, or that its light once filled an atmosphere strongly enough to turn the daytime sky blue. The disk has been lost for a very long time by this stage. The planets are compressed into angles far too small for unaided vision to separate. The brightness has now fallen into a range shared by many prominent stars. What remains is a single point among other points, distinct enough to identify but not distinct enough to announce itself as a sun. This is why Alpha Centauri offers one of the clearest visual answers to the question. From a nearby star system, the Sun truly becomes someone else's star. The reversal is simple but profound. From Earth, Alpha Centauri is part of the stellar background, a neighbouring system reduced by distance to points of light. From Alpha Centauri, the Sun would take on that same role. The relationship becomes symmetrical in appearance, even though the physical systems remain different. Each is a stellar source seen from the other across interstellar space. The concept of the Sun as central exists only from within the solar system. Outside it, there is no visual rule that preserves that status. The Sun is no longer the centre of the sky, no longer the source that determines day, and no longer the brightest object by an overwhelming margin. It is simply one luminous body at a known distance. The importance that once seemed built into its appearance is revealed as local perspective. At roughly 4.4 light-years, that perspective has been removed enough that the Sun can be placed naturally into the surrounding stellar population. A magnitude near plus 0.4 would make it brighter than many stars visible from Earth, but still far from unique. A dark sky contains numerous stars bright enough to catch the eye, and the Sun would join that class rather than sit above it. Its brightness would be comparable to the kind of prominent star that helps form recognizable constellations rather than the kind of source that erases constellations altogether. This is a crucial difference. Earlier, every comparison still carried a trace of solar exceptionalism. At 1 light-year, the Sun remained brighter than Sirius. Around 1.8 light-years, it fell to a Sirius-like level, but Sirius itself is exceptional. Near Alpha Centauri, another reduction in brightness places the Sun in a broader, more ordinary visual hierarchy. It still stands out, but it no longer owns the sky. The observer would need context to know what the point represents. Without prior knowledge, there would be no obvious reason to distinguish it emotionally or visually from other nearby stars. The Sun's spectrum could identify it as a star similar to many others. Precise measurements of its motion could locate it in three-dimensional space. Careful observations might reveal the gravitational effects or reflected light of planets. But none of those properties would recreate the direct experience of standing close enough for the Sun to have a visible face. Distance has transformed the source from an environment into a datum. It can be measured, classified, and placed on a stellar map, but it no longer fills perception. Earth becomes even harder to imagine from this point of view. The planet remains in orbit at 1 astronomical unit from the Sun, but at several light-years that separation projects into an extremely small angle. Its reflected light is faint compared with the star beside it, and the entire planetary system has become a subtle structure hidden around a bright central point. The distinction between an inhabited system and an uninhabited one would not be visible to the naked eye. Oceans do not make the Sun brighter. Forests do not alter its stellar shape. Cities do not change its place on the magnitude scale. A world full of life can remain concealed beside a star that looks completely ordinary from afar. This is the same difficulty faced whenever distant planetary systems are studied. The central star is usually easy to detect because it produces its own light. Planets are difficult because they are smaller, dimmer, and close to the star in angular separation. From Alpha Centauri, the solar system would inherit that same observational disguise. Jupiter and Saturn would not present themselves as giant worlds. Earth would not present itself as a blue planet. The whole system would require patient measurement before its architecture emerged. The Sun, meanwhile, would be the obvious feature and yet would reveal very little by itself. Its apparent ordinariness would hide an enormous amount of complexity. This is one reason the phrase, "just another star," can be scientifically useful even though it is not a strict category. A star can be ordinary in appearance while extraordinary in context. The Sun can look like one point among many and still host a planetary system with diverse worlds, a long dynamical history, and at least one planet where life has altered the atmosphere and surface. None of that is contradicted by the simple view from 4.4 light-years away. It is merely unresolved. The visual transformation, therefore, teaches something broader about astronomy. Distance does not only make objects smaller and fainter, it hides structure. It converts systems into sources and environments into measurements. The farther the observer travels from the Sun, the more information must be recovered indirectly. First, surface detail is lost. Then the disk itself disappears. Then planetary separation collapses. Then brightness no longer singles the Sun out as an exceptional local object. By the time the viewpoint reaches Alpha Centauri, nearly everything that once made the solar system visually obvious has been compressed into one modest stellar point. The only remaining path toward greater ordinariness is further fading. A magnitude near plus 0.4 is still relatively bright. The Sun would remain an easy naked-eye object under dark conditions, and a knowledgeable observer could locate it without difficulty. It has become another star, but not yet a faint one. That distinction matters because the journey has moved from categories of shape into categories of prominence. The Sun is now fully stellar in appearance. The next question is whether it can become visually unremarkable even among visible stars. To answer that, the distance must increase until the Sun reaches the standard benchmark used by astronomers to compare intrinsic stellar brightness. That benchmark is 10 parsecs, a little more than 32 light-years. At that distance, the Sun's apparent brightness becomes its absolute visual magnitude, about plus 4.83. The change between Alpha Centauri and that farther point will not alter the Sun's shape, because it is already unresolved. It will alter only its status within the stellar field. Near Alpha Centauri, the Sun is a bright star that no longer looks like a sun. Farther away, it will lose even that modest distinction and settle into the much larger population of stars that are visible but easy to overlook. The transition at 4.4 light-years, therefore, carries a different kind of finality. The Sun no longer needs to become smaller. It no longer needs to become point-like. It no longer needs to lose the visible architecture of its planetary system. Those changes are complete. What remains is brightness alone, and from the sky of a neighbouring stellar system, that brightness is already ordinary enough that the Sun has crossed the most intuitive version of the threshold. It has become a star among stars, with nothing in its naked eye appearance to reveal that one of those distant points once filled an entire world with daylight. At 10 parsecs from the Sun, the question of ordinariness finally reaches one of astronomy's standard measuring points. A parsec is a unit built from stellar parallax, the tiny apparent shift in the position of a nearby star as an observer changes location, and 10 parsecs correspond to roughly 32.6 light-years. This distance has a special role because astronomers define a star's absolute magnitude as the apparent magnitude it would have if it were placed exactly 10 parsecs away. For the Sun, that absolute visual magnitude is about plus 4.83. The number is important not because anything physical happens to the Sun at this distance, but because it places the star on the same brightness scale used to compare stellar luminosities without the confusion introduced by different distances. From Earth, a nearby star can look bright simply because it is close, while a far more luminous star may look faint because it is much farther away. Absolute magnitude removes that particular effect by imagining every star at the same standard distance. When the observer actually moves to 10 parsecs from the Sun, the hypothetical comparison becomes literal. The Sun appears with the brightness assigned to it by its own absolute magnitude, and the result is surprisingly modest. A star that once dominated the sky at minus 26.7 has faded to plus 4.83. It remains visible to unaided human vision under a dark sky, but it no longer belongs to the prominent structure of the heavens. It does not compete with the brightest stars. It does not resemble Sirius, Vega, or the brilliant points that immediately attract attention. It has entered the much larger population of stars that can be seen when conditions are good but can easily be overlooked. This is one of the strongest meanings of just another star. The Sun is not merely point-like now, because that transition occurred far earlier. It is not merely comparable with bright stars, because that happened within a few light-years. At 10 parsec, it has become ordinary in apparent brightness. A person scanning a dark stellar field without knowing where to look might pass over it without noticing anything unusual. Its light would not announce the presence of Earth. Its colour would not make it unique. Its position would matter only to someone carrying a map or measuring the sky carefully. The star still possesses all the physical properties it had near Earth, but visual prominence has been almost entirely removed by distance. This is where the difference between intrinsic luminosity and apparent brightness becomes especially useful. The Sun is not a dim star in an absolute sense, nor is it among the most luminous stars in the galaxy. It occupies a relatively moderate range for a main sequence star, converting hydrogen into helium in its core and radiating a stable output that has sustained the planets for billions of years. From 10 parsecs away, that intrinsic output produces a visual brightness near the lower end of comfortable naked eye visibility. The apparent faintness is therefore not a sign that the sun has weakened. It is simply the expected appearance of a star of solar luminosity viewed from several tens of light years away. This is the perspective astronomers routinely apply to other stars. A distant point can look unimpressive while representing an object enormously more powerful than anything familiar on Earth. The sun, finally placed at a typical stellar distance, becomes subject to the same perceptual compression. Its significance is hidden inside a modest amount of light. The solar system is hidden even more completely. From 32.6 light-years away, the angular separation between the Sun and Earth is extremely small. Jupiter's wider orbit helps somewhat, but the contrast between planetary reflected light and stellar light remains severe. The planets do not form a visible miniature system around the Sun to unaided vision. They are buried in the glare of the central point. A distant observer would need sensitive techniques to recover them. Motion of the Sun around the solar system's center of mass could reveal gravitational companions. Tiny periodic reductions in brightness could reveal a planet passing across the face of the star if the geometry happened to align. Direct imaging would demand instruments capable of suppressing the Sun's light while resolving the faint planetary signals nearby. The solar system, which appears expansive and richly structured from within, has become an observational problem. This is exactly how other planetary systems present themselves from Earth. A star may look simple while hiding multiple worlds. Its planets may span enormous distances and possess moons, atmospheres, rings, oceans, storms, and geological histories. Yet the system can still collapse into a point that appears almost featureless at first glance. From 10 parsecs, the Sun becomes part of that same problem. Its apparent ordinariness is not evidence of simplicity. It is evidence of distance. Even Earth's biological activity would not make the solar point visibly remarkable to the naked eye. Life alters Earth's atmosphere and surface, but those changes are confined to a planet whose light is vastly fainter than the star beside it. Detecting such signatures from tens of light years away would require careful observation of planetary light or spectra, not casual recognition of the Sun itself. The star would offer no obvious visual hint that one small world around it contains oceans, oxygen-rich air, or technological activity. The idea that the Sun becomes ordinary therefore carries an important observational lesson. Ordinary appearance can conceal extraordinary context. A modest star in a distant field may host a complicated planetary system, just as the Sun does. Nothing about visual prominence alone can settle that question. The magnitude scale reinforces this point because plus 4.83 is bright enough to remain visible but faint enough to disappear easily under poor conditions. From Earth, artificial light pollution can erase stars much brighter than the faintest objects theoretically visible to the eye. From a truly dark location, a star near magnitude plus 5 is accessible, but it does not dominate. It belongs to the texture of the sky rather than its main pattern. At 10 parsec, the Sun would inhabit that texture. Constellations built around brighter stars would draw attention elsewhere. The solar point might sit between more conspicuous neighbours, one modest source among many. If no label identified it, there would be no visual reason to linger on it. This is a much deeper form of anonymity than the earlier milestones provided. Near Alpha Centauri, the Sun was already another star, but still a relatively bright one. At 10 parsec, it is neither special in form nor striking in brightness. Its identity survives only through knowledge. Spectroscopy would reveal the characteristic pattern of a star like the Sun. Accurate measurements would establish its temperature, composition, motion, and luminosity. Observations over time could reveal planets, but the immediate sensory experience offers almost nothing distinctive. The journey outward has converted a source that once determined the entire cycle of day and night into a point that can be missed during a casual glance. There is a certain precision to this distance because 10 parsecs is not chosen for emotional effect. It is embedded in the way stellar brightness is defined. That makes the Sun's appearance here especially informative. It shows what the Sun looks like when stripped of the advantage of unusual proximity and placed into a standard astronomical comparison. The answer is not spectacular. It is a moderately faint star. This is the regime where the title question reaches its strongest statistical form. The Sun has entered the same observational category as countless other stars that populate dark skies without dominating them. Yet even this does not represent the end of the outward journey. Visibility remains, under favorable condition. The Sun can still be seen with unaided eyes at 10 parsecs. To erase even that final connection, the observer must travel farther until the apparent magnitude approaches the usual threshold of naked eye detection. That threshold is not exact, because human vision and sky quality vary, but it lies around magnitude +6 to +6.5 under excellent conditions. The Sun has therefore become ordinary before it becomes invisible. It can spend many light years as a modest background star, recognizable only because its position is known, before distance finally removes it from naked sight altogether, at 32.6 light years. However, the essential transformation is already complete. The nearby star that once seemed unique has been placed at the standard distance of stellar astronomy, and under that comparison, it reveals something almost quiet in its normality. The Sun is still there, still producing the same energy, still holding its planets in orbit, and still sustaining a distant Earth. But in the sky, it has become easy to overlook, around 70 light-years from the Sun. The transformation reaches its quietest visual threshold. The Sun has already become point-like, already fallen into the brightness range of ordinary stars, and already lost every naked eye clue that once marked it as the center of a planetary system. What remains now is simply visibility itself. Under exceptionally dark conditions, unaided human vision can detect stars down to roughly magnitude +6 or somewhat fainter, with a commonly cited practical limit near +6.5 for good eyes under very clear skies. The exact boundary is not universal. Atmospheric transparency, local sky brightness, eyesight, altitude, and even the amount of time the eye has spent adapting to darkness can change what remains visible. But the threshold provides a useful final landmark, with the Sun's absolute visual magnitude near +4.83. Increasing the distance to around 70 light-years pushes its apparent brightness close to the lower edge of what a person could normally detect without optical assistance, assuming interstellar dust does not add significant extra dimming along the line of sight. The result is almost difficult to reconcile with the Sun known from Earth. The same star that once overwhelmed the daytime sky has become a faint point requiring darkness and attention merely to be noticed. Nothing physical has happened to the Sun itself. Its core continues producing energy. Its photosphere continues radiating into space. Its planets continue moving around it. Earth remains in orbit at 1 astronomical unit, receiving nearly the same solar flux it always has on the timescale relevant to this imagined journey. Only the observer has moved far enough away that almost all of the Sun's apparent brightness has been diluted across distance, at 70 light-years. The inverse square decline has performed nearly all of the visual work it can perform for unaided human eyes. The Sun has not ceased shining. It has simply fallen beneath the sensitivity of ordinary vision. This distinction is important because disappearance from sight is not disappearance from reality. A modest telescope could still detect the Sun easily from farther away. Larger instruments could continue measuring its spectrum, temperature, motion, and composition across vastly greater distances. The star would remain scientifically accessible long after it had vanished from naked eye view. What changes at this threshold is only the direct human experience. Without instruments, the Sun would be gone. An observer scanning the sky would see many other stars and perhaps no sign at all of the one that once defined the word daylight. This is the final reversal of the perspective that began near Earth. At the starting point, other stars disappeared in the Sun's scattered light. Here, the Sun itself disappears among them. The magnitude scale makes the transition seem orderly, but perception turns it into something more abrupt. A star slightly brighter than the visual limit can be found with effort. A star slightly fainter may simply not register. The underlying brightness continues changing smoothly with distance, yet the observer experiences a threshold because the eye has a finite sensitivity. This is similar to the earlier loss of the solar disk. The angular diameter did not suddenly collapse to zero at Neptune or in the Kuiper Belt. It simply became too small for unaided vision to resolve. In the same way, the solar light does not suddenly stop arriving near 70 light-years. It becomes too faint for the unaided eye to distinguish from darkness and background noise. The two thresholds are separated by an enormous gulf in distance. The Sun becomes effectively point-like while the observer is still within the outer solar system, but it does not approach invisibility until dozens of light-years away. That gap is one of the clearest demonstrations of why apparent size and apparent brightness must be treated as separate questions. The disk is lost early, the light survives much longer, by 70 light-years. Even that surviving visual trace has become fragile. Interstellar extinction can complicate the exact distance. Dust between stars absorbs and scatters some visible light, and the amount depends on the particular line of sight. The local stellar neighbourhood is not uniformly opaque, so there is no single correction that applies equally in every direction. For the simple distance estimate, the cleanest assumption is to ignore significant extinction and consider only geometric dimming. Under that approximation, the Sun approaches the naked eye limit around the scale of several tens of light-years, with roughly 70 light-years providing a useful benchmark for a limiting magnitude near plus 6.5. The value should therefore be understood as a perceptual milestone rather than a sharp physical frontier. Some observers, under exceptional conditions, might retain naked eye visibility somewhat farther away. Under mediocre skies, the Sun would vanish much sooner. Light pollution alone can erase stars far brighter than the theoretical human limit, which means that a Sun visible from a pristine interstellar vantage point might already be invisible from a brighter environment. The deeper significance of the distance is not its exactness, but what it reveals about the Sun's place among stars. Once an observer has travelled tens of light-years away, the star has lost every special visual status conferred by proximity. It is no longer a disk. It is no longer the brightest point in the sky. It is no longer unusually bright compared with familiar stars. It is no longer even reliably visible. The solar system around it has been compressed into an angular scale requiring sophisticated observation, while Earth's reflected light remains extremely faint beside the star. A person looking toward the Sun from this distance would receive no immediate visual evidence that a habitable world lies there. The Sun could disappear from naked sight while Earth continued orbiting unseen beside it. This makes the threshold relevant to the wider problem of detecting life-bearing systems. A star need not look remarkable to host planets, and a planet need not be visible to exist. Distance hides complexity with extraordinary efficiency. At 70 light-years, the solar system would be one stellar system among many in the surrounding region of the Milky Way, and the Sun's modest intrinsic luminosity would not make it an obvious target merely from naked eye brightness. Knowledge would have to come from instruments. A telescope could collect enough photons to restore the star from apparent invisibility. Spectroscopy could spread those photons into wavelengths and reveal the fingerprints of elements in the solar atmosphere. Precise measurements could establish the Sun's motion. Sensitive observations could search for planets through their gravitational effects, periodic transits, or direct light if technology and geometry allowed. The Sun would not become scientifically lost simply because the unaided eye could no longer see it. Yet the sensory connection would be gone. No point in the sky would immediately identify the direction of Earth's star. That absence completes a progression that began with the most visually dominant object a human observer can experience. Near Earth, the Sun defines the difference between day and night. Near Neptune, it becomes tiny but remains overwhelming. In the distant solar system, it becomes a brilliant stellar point. At a light-year, it still outshines Sirius. Around a few light-years, it settles into the range of bright stars. At 10 parsecs, it becomes modest. By around 70 light-years, it reaches the edge of naked eye detection. Each stage removes another layer of apparent importance without altering the underlying star. That is the central lesson contained in the fading. The Sun is special to Earth because Earth is close to it. Its visual authority is local, not universal. From far enough away, the same star becomes faint enough to disappear entirely from ordinary human sight, while brighter and more luminous stars elsewhere continue to mark the sky. The transition does not diminish the Sun physically. It only places it in a larger context. A star capable of sustaining the energy budget of a living planet can still become invisible across a distance that remains small compared with the scale of the Milky Way. 70 light-years is only a tiny fraction of the galaxy's extent, yet it is enough to erase the Sun from unaided vision. The final threshold is therefore not where the Sun stops shining, but where human eyesight stops following it. Beyond that distance, the journey can continue indefinitely, but the star that once filled half a degree of sky has already vanished into darkness. There is no single distance at which the Sun becomes just another star. because the transformation happens in layers, and each layer answers a different version of the question. If the criterion is shape, the answer arrives surprisingly early, somewhere across the outer solar system, around a few tens of astronomical units from the Sun. The familiar solar disk becomes so small that unaided human vision can no longer comfortably distinguish it from a point. Near Neptune, and through the Kuiper Belt, the Sun begins to look stellar, even though its brightness remains extraordinary. From those distances, the star that once occupied about half a degree of sky has been compressed to around an arc-minute or less. Its surface is still physically enormous. Its photosphere still spans nearly 1.4 million kilometers, but angular size has done what distance always does. The disk has been reduced below the scale that matters for ordinary visual recognition. By that definition alone, the Sun has already become star-like before the observer has even left the broad outer architecture of the solar system. Yet this answer immediately feels incomplete because the point is still far too bright. A normal star in the night sky does not dominate illumination. It does not resemble a concentrated source of daylight. It does not remain visible with the overwhelming intensity the Sun still possesses beyond Neptune. So a second definition becomes necessary. If just another star means a point whose brightness resembles the brightest stars seen from Earth, then the journey must extend into interstellar space. Even 1 light-year is not quite enough. From that distance, the Sun would still appear brighter than Sirius, the brightest star in Earth's night sky. Only around 1 to 2 light-years does the apparent brightness begin to settle into the same broad range as the most brilliant familiar stars. Near roughly 1.8 light-years, the Sun would look similar in brightness to Sirius. That is a more satisfying threshold because both shape and brightness have now entered recognizably stellar territory. The Sun is no longer a disk, and no longer a source whose intensity seems completely incompatible with the nighttime sky. Still, it would remain conspicuous. Sirius itself is not ordinary in the sense of being easy to overlook. It stands out precisely because it is brighter than every other star in the terrestrial night. A sun with similar apparent brightness would therefore still attract attention. The next threshold lies farther away, around the distance of the Alpha Centauri system. From roughly 4.4 light-years, the Sun would appear as a bright but unexceptional stellar point. Its apparent magnitude would be around plus 0.4, placing it among stars that are easy to see but not visually dominant. This may be the most intuitive answer to the title because it reverses the perspective of the nearest neighbouring star system. From Earth, Alpha Centauri appears as distant starlight. From Alpha Centauri, the Sun would appear in much the same basic way, a point among other points, noticeable but not unique. Nothing in its naked eye shape would reveal that it once filled Earth's daytime sky, or that a small planet around it carries oceans and life. At that distance, the word Sun has become a local name rather than a visible category. The star does not look like the centre of anything. It looks like a star in a field of stars. Ava. So, astronomy offers a stricter measure of ordinariness. At Temporsich, roughly 32.6 light-years. The Sun reaches the distance used to define absolute magnitude. Its apparent visual magnitude there would be about plus 4.83. At this brightness, it remains visible under a sufficiently dark sky, but it is no longer prominent. It does not anchor a familiar pattern. It does not catch the eye immediately. It belongs to the dense background population of modest stars that fill dark skies and can easily be overlooked. This threshold is powerful because it removes the advantage of unusual proximity almost completely. The Sun is being judged at the same standard distance used to compare stellar luminosities. When placed there, it reveals itself as neither exceptionally brilliant nor especially faint. It becomes ordinary in the statistical and observational sense that matters to stellar astronomy. The point that once erased nearly every other star from the daytime sky has become one of many faint naked eye sources. Continue farther still, and even that modest visibility disappears, around several tens of light-years, with roughly 70 light-years providing a useful benchmark under ideal dark sky assumptions. The Sun approaches the usual limit of unaided human vision. The exact distance is not fixed because eyesight, sky brightness, atmospheric conditions, and interstellar dust can all shift the threshold, but the general result is clear. At a distance that remains tiny compared with the size of the Milky Way, the Sun can fade completely from naked sight. It still shines physically, It still radiates the same energy into space. Earth still moves around it, but an unaided observer looking back would no longer see the star at all. This final threshold exposes the full scale of the transformation. At Earth, the Sun is too bright to look at safely and large enough to resolve as a disk. At a few tens of astronomical units, it becomes point-like. Around a few light years, it becomes comparable with bright stars. At a few dozen light years, it becomes visually modest. By around 70 light years, it approaches invisibility to the unaided eye. None of these distances is more correct than the others. Each answers a different question hidden inside the phrase, "just another star." Geometry answers when the disk disappears. Photometry answers when the brightness becomes stellar. Comparison with nearby systems answers when the Sun loses obvious prominence. Absolute magnitude answers when it settles into an ordinary stellar range. Human vision answers when it disappears altogether. The lack of one exact boundary is not a weakness in the answer. It is the scientific point. Nature rarely respects categories built from human perception. The Sun does not cross a line and transform from sun into star. It is a star at every distance. Only the observer's relationship to it changes. Close enough, a star can fill part of the sky, warm a planet, scatter light through an atmosphere, and become the organizing center of an entire environment. Far enough away, the same object is reduced to a point. Farther still, that point becomes one among many. Farther again, it is lost without instruments. The star itself never needs to become smaller, colder, or weaker for any of this to happen. Distance alone removes its apparent uniqueness. That is perhaps the strangest part of the journey. The Sun does not become ordinary because something happens to it. It becomes ordinary because everything that once made it seem special belonged to perspective. The broad disk, the daylight, the warmth, the overpowering brightness, and the apparent centrality of the solar system all depend on occupying a small region close to one particular star. Leave that region, and those properties separate one by one until almost nothing remains except a point of light with a known position. From another star system, the Sun could be catalogued, measured, classified, and perhaps examined for planets. Yet no casual glance would reveal its relationship to Earth. The oceans, clouds, forests, deserts, and cities of the inner system would be hidden beside it. The entire human history of the sky would be compressed into a source that looks ordinary from afar. That is the visual paradox at the center of the question. The Sun is the brightest and most consequential object in Earth's sky, yet neither brightness nor consequence follows it universally. Travel far enough, and the star that once divided day from night becomes a small point among countless others. Travel farther still, and even that point disappears, while the galaxy continues around it unchanged. What seemed like the central light of the sky was always one star seen from very close range. There is something quietly useful in the fact that the Sun never truly changes during this journey. The light weakens, the disk contracts, the planets crowd closer to its position, and eventually the familiar source of daylight becomes only one faint point among many. Yet the star itself remains what it always was. The transformation belongs to distance. Close to Earth, proximity gives the Sun an appearance that seems unique, a visible surface, overwhelming brightness, warmth, and the power to shape the entire sky. Farther away, those qualities separate and fade at different rates until the underlying simplicity becomes clear. The Sun is a star, and Earth happens to orbit close enough for that star to feel like something more. Beyond the outer planets, its face is lost. Across interstellar space, its brightness settles gradually into the ordinary hierarchy of stellar light. From several dozen light years away, even a careful naked eye search may no longer recover it at all. Yet somewhere beside that faint or invisible point, Earth continues circling at the same small distance, receiving the same nearby sunlight and experiencing a sky in which the Sun still rises broad and brilliant. Both views are true at once. One depends on standing close enough for a star to dominate everything. The other depends on moving far enough away for the galaxy to restore proportion. In that larger setting, the Sun does not become less real or less important to the worlds around it. it simply becomes harder to distinguish from the countless other stars scattered through the Milky Way, each one defined by its own distance, brightness, history, and perhaps by systems that remain hidden beside its light. The familiar sun eventually becomes another star not because it has lost anything, but because distance has revealed what it was from the beginning.